All right, picture this. It's March 2020. Everybody just went to work from home. You work at Slack, which is suddenly one of 3 applications keeping the entire business world connected. And nobody owns Memcache. Today's episode of Turn Stories is with Glen Sanford, who decided he was going to own Memcache and he was going to migrate it. I am stretching that word today. Glen migrated Memcache from bad to okay, and then from okay to good. This is a story of good old-fashioned engineering in one of the highest volume components in an application that you've probably used in the last 20 minutes. So we're going to talk about cap theorem. We're going to talk about what a modern observability stack really does for an engineer, and Dunkin' Donuts. Let's go. On today's episode, I've got Glen Sanford with me. Glen was originally a history major, but he's worked at companies like TiVo and Twitter. He founded a company at Turbine Labs, which is where I got to know you. And then we both worked at Slack together, where he was on the infrastructure team. So welcome, Glen.
Hello. It's nice to be here.
So you've worked at a bunch of impressive companies. Tell me a little bit about the kind of stuff you worked on. I imagine, I would imagine just based on that resume, it's obviously all front end and UX, right?
Right. Yeah. No, it's been a fun ride. I actually did some front end throughout my career here and there. I've done some, but and I started my career as a front end coder before I went back to school for CS. Because back then, front end was just not something you needed any kind of bona fides for. You just showed up and said, I could do HTML, and they would hire you. And that's kind of true now, but you still have to, I don't know, have a resume or something. .com times were wild.
We could do a whole episode on how front end is now real engineering and believed to be so.
And right, yeah, and but it's been a 2-decade transformation for it to be taken seriously as a practice, and I'm all for it. But in the meantime, I did a bunch of backend coding. So yeah, TiVo was right out of school, and I spent 5 years there and kind of learned how to be an engineer of any kind, and work on deadline and work with people and write documents and do all the things engineers do. And I learned a lot about my mentor there was really into every system should just be this one box, and you just have n of them, and make it simple little boxes that do things, which wasn't microservices yet because it was 2005, but looked a lot like microservices later on.
A word yet to be invented.
It was invented during the time I was at Twitter, and we also started into service-oriented, it was service-oriented architecture before that. And somebody decided we should make them smaller and have lots more of them. But Twitter was where I think I really learned kind of big system chops. I went from when something's broken, I go and look at the logs, to when something's broken, I go and look at the metrics. And because you can't look at logs when you're processing, 15 million requests a second, because the logs there's just too many logs, right? You can't tail a log file to learn anything. Later on, a couple of years later, now you can dump it all into Honeycomb and structure analysis and do all that stuff. But it was we can count things at our pace. At 2010, we can count things and we can say this many things went wrong. So Twitter was fun.
What was the service you worked on at Twitter?
So at Twitter, I worked on a couple of services, but I was sort of fortunate to be in this team of folks who sort of accidentally found themselves rewriting all of the core business logic as we migrated stuff out of the Rails monolith and into Scala-based services. And so I wrote the authorization service there first, which it was it was actually one of the first services that had been carved out of the monolith and kind of just withered on the vine for a year or two because we couldn't use it yet. We had nothing. We had no back-end services to auth with it, and no front end. We also separately were writing a front end, kind of think Envoy, but sort of Envoy, that where the auth would live, but we didn't have the front end yet either. So anyhow, so I wrote that sat there, and then I contributed a lot to the user service there, which we called GizmoDuck for no good reason. And you think of every time you need to turn a screen name into a user ID or find out how many followers they have or do anything about a user, we were the service you would call. And I think when I left, we were doing 15 or so million user lookups per second, because you really need a user for everything. And often you need like 10 users. Like our average width was 10 users at a time. That was a fun service to build. We wrote it, and then like the entire time I worked on it, I also managed the team that worked on it for a little while there. The entire time I worked on it, we were just migrating the service from like one way it worked to another way it worked to another way it worked. It was like, and it was sort of there that I developed an understanding of infrastructure engineering as kind of a constant migration from one thing to another as business requirements change, as technology becomes available and old stuff looks older.
Which seems relevant
Yeah.
as you tackled stuff at Slack. So the migration that I want to talk about today is you had. I feel like I'm interested in this, but we were both there at Slack at the time, and there was this enormous amount of work that went into Memcache, which is extremely at the core of Slack. So
it's true. So yeah, let me talk about how I found myself thinking about that, because I didn't get there immediately. I'll try to be as brief as I can. But we joined Slack, and you and I both, in 2018, and the first project I worked, Slack had just gone through this shift that a lot of companies go through from I press a button and I deploy everything all at once. And YOLO, things happen, but like it's a small company, who cares, to like when I press that button, it causes a massive site outage for everybody for a minute. And so I need to be more deliberate and careful about my software rollout. And also, sometimes when I press that button, everything breaks and rolling back is harder and more dangerous than it used to be, et cetera. So they had moved to this staged deployment process that took half an hour. And all of a sudden, everything that they had stored in config files that were checked in, like what host to talk to where, that they could change instantly, now they have to, it takes an hour for them to change it. And that was totally like, so when your database goes down and you need to patch the file to talk to some other database, because I didn't have service discovery yet, that used to be something you could just go do. Like you get paged and you wake up in the middle of the night and you press a button and you fix it. And now you have to do a deployment that takes 30 or 40 minutes. And so that was a problem. And so there were a bunch of interesting problems that fell out of that in the kind of configuration plane of the Slack application for things that needed to get carved out and made faster. And so the first project I worked on when I got there was this system for shipping database configuration around that could be changed instantly. And it was like this very simple, like write a file to S3 and twiddle a little thing and key in console that everybody's watching. And now everybody downloads the new file. And so it felt like a really powerful lever that I sort of had incidentally been shown. And then I got pulled up onto, very briefly, I was assigned to Memcache then in my first couple of months. And it was like, hey, nobody owns Memcache. Do you want to own Memcache? And I was like, absolutely. That's the no.
that is not the right answer, way to solve the instability of a service.
The answer to nobody owns this, do you personally want to own it, is always no. Should never, that always no. But I agreed to sort of look at it and take a crack at sort of identifying some things that might be improved. And I pitched some work that was interesting work to do, but that like was so much lower priority than almost anything else we could do that immediately something else shiny happened and I was moved on to some other project. And Memcache
room. What do you think was the motivation of like, was there just like, if there is known, I don't want to say instability, but there are known problems with Memcache. Like what's the rubric that the business was using at that point to figure out like, yeah, that's not worth fixing. We're just going to let it burn.
I don't think it was even that careful in its analysis. I think Memcache is a thing, and we should do an aside to talk about what it is and what it does like for a minute, but so pin that. But Memcache is a thing that as a system, it's fairly simple conceptually, and mostly it doesn't, their implementation didn't break mostly. And when it did, it was spectacular. But you could sort of like, there was never a set of people who could reasonably be assigned to fix it, because there was in the growing company always other things to that were more important to scale out. Like that, there's this enormous database migration that Slack underwent from this kind of dual master replication thing to Vitesse, and that was always more important than anything else. Like getting that migration going, and then just running Vitesse was always more important than anything else. Let's take a minute though. Let's take like 2 minutes. What's Memcache? Because honestly, it's like in the depths of things for a lot of people now.
Yeah, I guess what is Memcache, and then what is Memcache at Slack? Because I think the answer to that is slightly different.
Both good. So I'm going to talk about different pieces of that stack throughout while we're talking. So Memcache is a very simple little binary that stores key value mappings in memory. So you say set this key to this value, and you can say get this key. There's the protocol is more complicated than that, but not a lot more complicated than that. And it's a text protocol. It's very simple, just over TCP. It's like a dead simple service. And that's kind of why I think it has endured, is that that part of it is rock solid and really hard to get wrong. So I'll talk a little. So there's LAMP stack. So we talked about LAMP. Does anybody remember LAMP?
What is a LAMP stack? For those of us who never experienced
a LAMP stack was how you built websites in 2008 or maybe or 7, and it was Linux, Apache, MySQL, PHP, and there was like a little lowercase m after the big M that was Memcache, because Memcache was the first thing you would drop in when you started to need the database to be faster than it could be, because reading from memory is faster than reading from disks. So the conventional wisdom in the development universe of LAMP stacks back then was just slap Memcache on it and it'll be fine, right? And PHP made this fairly easy to do. PHP had native Memcache bindings that you could just, so it was really easy.
Easy.
And so Memcache is great as long as what you need to store in memory stays in memory on the one box, or you don't need high availability. And life gets kind of weird when neither of those is true anymore. And Memcache provides itself, it or at least until recently, provides no affordance for like, want to have 10 Memcaches and I want to stripe my data across them, or any kind of it naively supports horizontal scaling because you can always add more Memcaches, but you need more complexity to support that scaling. And so there's this you need something basically to spread the data across those Memcaches. And that's typically called the standard thing to do there is called consistent hashing, where you imagine your Memcaches as a circle, a ring, and you hash the keys in some one-way function that is purposefully built to distribute keys evenly across that ring, and in particular to distribute them so that when you add new hosts to that ring, there are some guarantees about where the data goes so that you don't end up with like weird inconsistency problems. So you need some software for doing that hashing and spreading it out and knowing what the hosts are and all that stuff. And so there's this thing that Facebook wrote that Slack used called McRouter, with a Mic there is Memcache. And it does a lot of the routing for you. Its configuration file is in JSON, and it just goes off and does its thing. So Slack used McRouter because Slack also was halfway through a migration from PHP to Hack, which is the Facebook invented PHP but type checked language, and so they were kind of just on the Facebook technology train. So you got your Memcache, you got your McRouter, and you had your config file that was just existed. We were talking about deployments a minute ago. How your web apps knew what memcaches to talk to was a thing, was fixed in space checked in, and whenever anything went wrong, you would just add a new host or whatever. And that broke as soon as the stage deployment went in. So there was this really wonky old Python 2 system that that good engineers wrote in a hurry because they had to. I don't want to offend anybody. It was exactly the situation that was needed, and then it lasted for years and years and years and years.
Longer than it maybe should have, but
yeah,
that's positive on the engineers that wrote it, right?
Maybe it was a system of leader election that would basically allow the memcaches to wake up and say, I'm going to occupy this slot in the consistent hashing ring, and then that was all written into console, and then everywhere where you needed that routing information, you had console template rendering a config file. It was kind of a mess. Anyway, so that I have blurred into a discussion of Memcache and into a discussion of Slack's usage of Memcache, but I think you get the idea.
Yeah, the fundamental point is that Memcache is something. The Memcache, the technology, is built for a single host, and there's not many affordances within the core technology. And Slack's use of Memcache was fundamentally about being able to use more than one machine to cache its data. So, hence McRouter and the usage there. And we were talking about how you'd seen some problems with the deploy here, right after you joined Slack, and they were promptly deprioritized, and you were told to do something else, if not own the whole thing. But we did decide to do this show because you did do a bunch of work on Memcache.
Right.
So what changed?
Well, so Memcache was kind of I refer to it as a volunteer firefighter organization that ran Memcache for a little while. And eventually it got reorged over to the data stores team. And I think the reasoning was every time Memcache breaks, you guys get paged, so you should own it.
Sure.
And the organizational problem with that is they got paged a lot and they never had time to do anything other than sort of poke at it with a stick and say, like, why you break. And so I think there was this kind of... So I went off and worked on the asynchronous job queue for a little while, and I'm going to just take 1 minute to say that that hammer I was talking about, the lever earlier about delivering dynamic configuration, I was able to take that lever and apply it to configuring this job queue in a way that convinced me that it was like a really useful, repeatable pattern for owning distributed configuration for a service. Through an accident of hyper growth, my manager took on the data stores team, and then there was this like spectacular confluence of different incidents that resulted in someone saying we should add load shedding to McRouter, as in a way that felt. I'll talk about why that was not a possible thing to do, but somehow they said it loud enough in a way to manifest funding to get some people together. And so my boss was like, this is kind of like can you go and figure out if there's any there, and can you sort of collect a team of people together to work on this sort of stuff for a little while? And so they called it a squad because infrastructure organizations have a tough time reorging quickly. So I had myself and a few other people who were all looking at kind of load shedding related things. And I was sort of nominally running that roadmap for a little while. And what super quickly became apparent to me was that like there was so much wrong with the Memcache stack that fixing this one piece of it that was being proposed to fix was like A, insufficient, and B, like actually totally impossible. And we just were going to I kind of used that project as a shield to say, I'm going to spend 18 months or 2 years on this and I'm going to fix it, where fix means make it operable and understandable and really chiefly owned by a team that is well positioned to do something useful with it and keep it running and not be terrified every time it breaks. I didn't have any guarantees that I was going to be able to do any of that, but that was my exit criteria. Was I'm going to work on this. I'm not going to take the pager for it. because it's just me. So data stores kept the pager. And my sort of solemn oath to them was like, I'm not going to make it any worse for you. I'm going to make it better until it's something manageable, and then I'm going to take it away from you. And they were so pleased to just not have to think about it for a while that worked fine. So
cool. So we sort of arrive at the beginning where you had.
Yes, sorry, it took so long.
No, I mean, this is. I mean, a big question of every migration is like, why are you doing this? Because if you're going to have someone spend years of their life on it, that it is worth understanding that.
And what I saw when I finally was able to look at it is there was so much wrong that you could sort of, there were multiple things, big changes that needed to happen. And so the biggest challenge I think initially was like, how do we figure out what to do first?
Mm-hmm.
How do we stage it in a way that feels sort of safe? And how do we not sign ourselves up to do things that we can't actually do yet because there's other stuff in the way? A useful organizational approach to this that I adopted from Twitter is this thing called good, bad, okay. Which
tell me about that. What's
good,
that?
bad, okay is so good. A colleague of mine at Twitter named Ryan Greenberg invented this, or at least co-opted it in a way that felt like invention within the company. I don't know which. And it was this way of describing an effort as a transition from one state to another. And the three possible states are bad, okay, and good. And the idea was that if you could honestly with yourself talk about which of those state transitions your job felt into, you could prioritize it, right? So like, if you think about it, like you never want to go from okay to okay. Like my thing is fine, and this other thing is going to be also fine, differently fine. Right? Like that's a waste of time, probably.
That doesn't seem worth doing.
Right. But the biggest one for me is you never want to start working on good until you've fixed all the things that are bad. Like find all the bad things and make them okay before you try to make anything good, because otherwise you're going to be working against yourself, because you're going to be supporting all those bad things as you try to make the good. Like that was the trap I think data stores fell into, is that they were like, there was so much bad, there was no chance to make anything good. They were just kind of cyclically fighting themselves.
You need to buy your own bandwidth to go work on the thing that you want to go work on, no matter how good the end result will be, that if you can't work on it, you can't get it done.
Yeah.
Doesn't matter.
And so you obviously don't want to go from good to okay or okay to bad. I think those are self-explanatory. But the one that I think is subtle is you don't really usually want to go from bad to good. You want to have an okay step in the middle, or several okay steps in the middle, because when you go from bad to good, you introduce various axes of risk, right? The biggest of like all the second system failures of where like, we're going to make everything better this time. We're going to fix it all. There's this enormous schedule risk that you bring in when you say we're going to fix it all with a new system. That's a kind of bad to good. So the trick with Memcache here was, let's articulate all the bads, and then let's figure out which of them is like both like truly bad and tractable to fix. And let's fix that stuff first. And let's fix all of that bad stuff before we start to try make any part of it good. And going back, that the doc I wrote when I first got there was actually an articulation of a good future state. And like, I really wanted to get there. But I was like literal years away from getting there. And so it was just like, how do we chart that course? How do we navigate our way there?
As you're thinking about, you've got your good desired state. Where was, and you've got your bad current state, which I don't think you said out loud, but this was also around 2020. So there was a wild uptick in traffic as well, right?
Yeah. This was about 6 months after the big step up. And like, but we hadn't really recovered, and everything was kind of on fire all the time.
So there was an obvious bad state in just like the sudden step change scale that COVID drove,
sort of externally bad. Yeah. How
did you think about like the good state? Like, what did the good state look like with that as the problem statement?
Well, so to me, the think it's worth just articulating some of the things that were the bad state, and then we could talk about what would have looked good in comparison. So the biggest bad state was inconsistent staffing. We were under this really tight deadline from a external customer to encrypt all of our traffic, which is a good idea anyway, because it's got messages and users and like all kinds of stuff that you really don't want in plain text, even over a controlled private network. So we needed to encrypt our traffic. McRouter, I mentioned, was running on this 4-year-old build that somebody had sort of like cobbled together with a couple of patches on top of the open source project, and we had no way to deploy it or update it or anything. There was no observability, really. We had no idea. Like, there was kind of this hodgepodge of different ways of looking at it, but we couldn't see it, and that was a big problem. It broke all the time, except when it didn't, but nobody wanted to touch it because when you touch it, it breaks all the time. And then there was just this kind of many different layers of attempts to fix it by trying things, like many different experiments layered on top of each other. Like we had multiple different versions of McRouter sidecars running on the web apps. We had 2 of them, one in TCP and one in socket. And then also the web app had a built-in McRouter that would talk to them. And then also it was just this, a lot of like, what if we tried this, but then never finished? And that's like because of the staffing problems. So there was a lot of like just stuff to machete out, but how do you do it on it's repairing the plane in flight, right?
The plane that has multiple smaller planes inside it because we thought maybe adding more wings.
Yeah. So, I mean, so you can see a good state is like, there's a team there. The traffic is encrypted. We have a single version of McRouter running that's up to date. We have enough observability to understand what's going on. We no longer run on a 2 versions old Python leader election emergency script from 4 years ago for configuration management. We'd like to be able to do things like actually change the configuration of McRouter dynamically, so that we can do interesting things like availability zone isolation and stuff like that. Really interesting stuff that you can't do if you can't ever change the config file, because the thing that uses the config file is 4 years old and the system that delivers the config file is cobbled together. And so that lots there, but like I said, you start with all the stuff that's truly bad and work your way there. And the 2 things that were truly bad for us, one of them was like a smell, and one of them was business. And the business was we had to get the traffic encrypted, because we had just like this hard deadline for a customer who was like not going to sign up with us if we didn't do this. Had to happen. Business requirement must happen. Had to happen. And then the other one was we really wanted to upgrade McRouter to we wanted one single version of McRouter running. We hypothesized that it would solve problems, but we knew that the original, if you'll recall, the original proposition for the team was, can't you add load shedding in McRouter? And the answer was absolutely not, until we could build it with you can't. Sure. You can't go and modify code until you can build it and deploy it, right? Or you can, but it's a thought exercise, right? So, so that was our lowest other tier bad was get McRouter to a point where we can build and deploy it and even think about making changes to it. And so I took on the encryption thing. My colleague, Mark McBride, who I imagine will be a future guest. He was my co-founder at Turbine and an old friend. And also was at Slack with us. He took on the McRouter, and I'm going to talk mostly about Nebula to start with, and then I'm going to hand wave over his McRouter work because he's much closer to it than I was.
We'll have to get him on the show. I'll ask him about it.
It's some good. There's a lot of good stuff in there, but so
Nebula. What is Nebula?
Yeah, let's talk about Nebula. So there's lots of ways to encrypt traffic. And the sort of most common one is probably SSL and TLS. So you have a cert and I have a cert, and we talk to each other to negotiate a key, and then we send traffic with that key. That's a kind of heavyweight for provisioning new hardware, because you have to have a cert for every host that you provision. it's hard to adopt. It's hard to make all systems support TLS broadly, right? Some of them support it better than others, but it's a headache. And Nebula was sort of invented to make that headache go away. It's a system kind of conceptually similar to a VPN, but it's basically like an encryption system that looks like another network device on your box. So it looks like your other Ethernet. But when you talk to that Ethernet, the data is guaranteed to be encrypted. And I'm not take a brief side to talk about the security staff, the security folks at Slack, the network security team. Really good, smart people, and understood that the company were customers of their effort as opposed to the other way around.
Yeah, it's such an important distinction.
Right. And then they understood that like their job is to make everything secure, but the company's job is to like ship products and do their jobs. And so if you're constantly saying, you got to fix this, do this, do that, do this is wrong, you're bad, that's not a good feeling for anybody. So they were really, really exceptional at trying to find ways to make it less onerous for customers to solve the problems that they legally needed to solve for security. And Nebula, I think, is sort of that made real in tech, in that it mostly just worked. And it wasn't very heavyweight. Like all you had to do was turn it on, and the system would sort of negotiate the keys and figure everything. There was a lighthouse that would distribute them or something. I don't know. I never really spent the time to figure out how it worked because I didn't have time.
You didn't have to, and that's half the point.
Right.
It's another interface. Use the interface and your traffic will be encrypted.
Right. And for so Memcache was fairly late on the adoption curve, mostly because it didn't work for Memcache very well. And so they had tried to turn it on for, I think we were in like the third year of attempts to turn on Nebula for Memcache. And what's really unique about Memcache, more than almost any other service in the system, is it's incredibly high bandwidth, right? So like the usage of Memcache went from like, there's this one thing that we look up in the database a lot, let's put it in cache and then it'll be faster, to cache is the thing that keeps our entire data set from knocking over the database all the time. And so the usage is incredibly high. And like every Slack API request has 10 or 20 or 100 Memcache requests under the hood. And they all are super fast. And some of them have a lot more data than you'd think. Like people store all kinds of weird stuff in cache. And Slack was not a place that was super into, it was not possible to enforce usage restrictions really in cache. They're just the team grew up too fast, and the people who owned the cache didn't even know they owned it really. And so people just put all kinds of weird stuff in there. And so it turns out that the hard part of making that system work is that you have to encrypt all of that network bandwidth, and that costs CPU. And I just don't think anybody had the time to sit down and figure out how much CPU it was going to cost for Memcache, because for every other system that they had used Nebula for, it was kind of just fine. Like their CPU went up a little bit, but the bandwidth, the amount of extra effort required to encrypt all the traffic back and forth, made Memcache sad, and also made the web apps that were doing the same encryption very sad. Right, like on both sides of that network boundary, it was harder. But especially on the Memcache side, because it was handling multiple requests from all the different web apps. Okay, so they turn it on, it breaks. They turn it on, it breaks. They turn it on, it breaks. And my boss just said, "I need you to go figure out why it breaks. Like this is like we can't.
The traffic needs to be encrypted." So when you say it breaks, what?
Yeah. So the first thing I did was I built a load test for it, where using this really fun thing called MemaSlap, which is there was a memc slap, which sort of makes sense. It was Memcache slap, and then somebody wrote a better version of it called MemaSlap, and it was this. It's now very old tooling, but so I like rolled it up into a little container and I put it in Kubernetes network, and I brought up some memcaches and I slapped them around, and I turned on Nebula and I slapped them around, and crucially, I checked the tool in and I wrote some documentation for it, and that was super handy down the road. So I'll foreshadow that. But what I found was that it didn't matter what hardware you were on. When you saturated Nebula, you were only able to use 2 cores, 200% CPU, 2 full cores. And in talking to the security people, I learned that it was a sort of, they had a thread for reading traffic and a thread for writing traffic, because that was enough for almost anything. It was written in Go. But that meant that, like, it kind of doesn't matter how good your hardware is or how many cores you have. You're only going to use 2 of them for Nebula, and you're going to use them all the way. And so what I found was I found some hardware that had slightly faster single CPU speed. And I found that if I got 16 core boxes with 4 cores over here for Memcache and 2 over here for Nebula, they would mostly not step on each other. That would minimize crosstalk. The cores didn't do any good CPU wise, but they sort of like encouraged the OS not to schedule those 2 things in the same place. And that was the best I could do. And what was going to happen was we were going to need so much more hardware. Just so much. And so I said,
what were you starting? Like, give me a sense of order of magnitude. Do you need 20% more?
Let me see what I can find. Yeah, I think we went from like needing like, yeah, here I have the numbers. We started with 180 active hosts and 50 spares. And these were R5 2x larges. So these are memory intensive machines, but not super high CPU wise. They're 2x is not that big. And we went to 540 with 180 spares, and there's C5N 4x larges. So there's 16 cores. There's like compute oriented hardware, and you have enough memory because of course you do, because you have so much hardware now. Right.
But, and the CPUs, if I was hearing you correctly, the CPUs are half idle because all you're doing is encouraging
mostly idle
scheduler.
Yes. And so I was like, and this is like, my boss and I used to joke that my job was to figure out ways to spend money to solve problems.
Well, congratulations.
And so this was and here's the thing though, it seems like a lot. It was still about 8% of what we were spending on storage. And my internal heuristic is like, if you spend 10% on cache to save the rest of your storage from completely falling over, that's probably makes business sense. Right. And so in my head, I was like, I got to stay under that 10%, but as long as I can say to someone with a straight face, like, this is 10% of what you're spending on disk, that seems okay. That seems fine, especially if it's getting us to this customer requirement.
Not bad, not good, but okay.
Yeah. All right. So we did this. And this was the first time. So growing the ring, we talked about the cache ring. Every time you replace a host in the cache ring, that host comes up cold with nothing in its cache, right? So it's got to fill up. And there's this period of time where things are trivially slower because some percentage of your traffic is falling through to disk because the data isn't in Memcache yet. Okay. So when you grow the ring, it's kind of the same thing, right? You're widening the ring by 1, which means now whatever that percentage of traffic is doesn't go to all those other hosts now as it goes to your new one. And so that new one comes up cold. So there's a pace at which you can do this. If you do it too fast, then the database melts down. And if you do it too slow, it just takes a million years, which is not so. So I kind of figured out what this was, and I went off and like did something 500 times, right? I wrote a script for it, because you write a script for things, right? But you had to be careful because the script required like, do you want to do this now? Yes, right. And then I go look at charts, and then yes, and then I look at charts and wait 2 more minutes and click yes, and then it gradually widens the ring to 540. And I did the same thing to swap the existing old hardware to the new hardware. It's a whole thing. I did this the first time, and like immediately upon having done this, there was a set of security tickets that required us to rebuild the whole cluster. Like it was going to be easier we couldn't apply the security patches. We needed new hardware. And so I had to go and restart that whole ring of 540 hosts again at that same, like I could do it every 90 seconds. I could press the button. And
Now
my
3
wife
times
is
longer.
like, can't you get computers to do this for you? And I was like, no, because you need a human to go and look at charts and say, it's okay to do it next. Do the next one. And so we referred to this process as making the donuts from the old 80s Dunkin' Donuts cartoon or a commercial where the guy wakes with the mustache. He's like, time to make the donuts. And I get real good at making donuts. I rebuilt that cluster probably 20 times over the course of the next year for various reasons. I fixed that eventually, but okay. So we turned Nebula on. We're slowly, right? We did 10%, 20%, 30%, 50%, 75%. We get to 75. Everything's looking good. We go to 100. Everything falls over, explodes. Total ruin. And so we had to.
Why?
We had to turn it back off. And I was talking about observability before. So we turned it all back off, and we're like literally dead in the water. We have no path forward on how to get this done. And so we start figuring out how we can see things better. We have some hypotheses about what might have gone wrong. But the biggest is that the metrics we have all measure per second, right? And so we can see a lot of them are per minute, but we can see like spikes in traffic at the second level. We can tell that at the top of every hour, for example, there's this enormous spike in traffic over the first few seconds. But we don't have a lot of observability into like what kinds of keys are being accessed and when and how often. And our hypothesis is that there are hidden in here some very high throughput request patterns that we don't understand. And in fact, we already have some of these. Like we know, like one of our biggest customers' keys, the workspace ID key gets looked up all the time, like literally hundreds of millions of times per second. And so we actually store that in memory on the web apps most of the time.
Right? Oh, wild. Interesting.
Host level caching. And because we know it would just destroy, even in plain text, it would just destroy the memcaches instantly, because all of that traffic, the way the keys are distributed, when you look up one key, you're talking to one memcache host and all that whole pile. And so
it doesn't matter if you have 500 instances, that one host is going to get every single request.
Is screwed, right? And that one host is extra in trouble now because it's got to hand back that key encrypted, and so it's just immediately going to saturate those two cores, right? Like you're just done. So we theorized that there was some access patterns that we didn't understand that we needed to, and so we started in on. Here's where I want to talk a little bit about build versus buy, just really quickly, and say that, and also plug Honeycomb as a product. So Honeycomb is a product for collecting traces or structured log events, and with very high cardinality in terms of labeling, and being able to query them and show charts at like a sub-second granularity. It was per minute. So our old metrics were per minute, and that was totally useless. So we wanted to get down into seconds and milliseconds, and Honeycomb was the tool for this. And it's the sort of thing that like Twitter built their Honeycomb because they had to, because Honeycomb didn't exist yet. No one should ever build that again in a company. People should use Honeycomb, or hopefully there will be one or more competitors, but I think Datadog kind of does something similar now.
We actually had Ian on the show last week talking about how Datadog specifically built a system that is, right, equal or better depending on who you ask to the Honeycomb backend. So
yeah, and
absolutely
great. But they're a company whose lifeblood is a system like that, right? So they had better had a good one, right? Yeah. And but like,
and they do
Slack,
it's big migration.
Like Twitter should not build that. Slack should not build that. Like no one should build that sort of time series, high cardinality labeled time series database ever again. And I believe there are whole classes of software for which this is just true. And everybody wants to build that because it's fun. But you cannot, as a business, support building that anymore. And in particular, even if it seems like it's going to be easy to build, you're paying a long-term fee to support and maintain a system and own it. And like, just don't do that. Pay Honeycomb, pay Datadog. Don't ever do that again. Anyway, Honeycomb was transformative for us in terms of what we could see. And in particular, because we could label every point, like we instrumented every single operation, and we labeled it with key prefix and key suffix and all sorts of other labels, because Honeycomb charges by the point, not by the number of labels on the point. So we just threw the book at it. And what was amazing was that we could then go and slice and dice all this stuff and figure out where's the bad traffic coming. And we found a bunch of keys that, and it was keys like the one I talked about, that were accessed literally like in millions of times per second.
Wild. Why? Why did Slack have those keys?
I don't. So, I mean, it's not that hard to think of it. Like, so you have a large Slack workspace. I don't want to name names because I'm not sure which customers are public and which aren't. But imagine large organizations you've heard of use Slack, and one of the things you do when you use Slack is you look up the workspace you're in. Right? You do that often because workspaces change, things change. And so it turns out that every user of those companies is looking up that data often. And it's just, there's a lot of people on there. There's hundreds of thousands of humans whose Slack clients are doing that. But really what gets you is the bots. There's like the Google Calendar bot at the top of every hour for every user who has it configured is going to go look up that workspace, and it's going to go look up a bunch of other stuff all at the same time, but from the clients. It's sort of a recipe for DOS. And it's always going to end up DOSing like these poor single memcaches that are hosting this key. And there is a whole side discussion of why is that? That seems like a dumb way to do it. And yes, it is. It's a dumb way to do it. That key should live in a few places. And it's just Memcache, by virtue of its very simplicity, makes it a little harder to do things correctly that way. And as soon as you have it living in multiple keys, now you have to solve the problem of consistency across those different hosts. And there's like a whole bunch of gnarly stuff that is why people now have all these other storage solutions for cache. You work with the system you've got. Anyhow, so we found some of these keys, we fixed them, we put them in the host cache I was talking about, so that the web apps just had a lot of these very common keys in memory all the time. We also, our friends at SecOps had developed a new version of Nebula that could use multiple cores to do its encryption. Like it could have multiple dedicated threads for both encryption and decryption. So all of a sudden we had like the observability to tell us all these access patterns that were terrible, and we're like, it doesn't matter how fast your host is if you're going to be asked to do something a million times. Like we had to fix those. We fixed the hotkeys. Mm-hmm. And then we got this new version of Nebula running, and it's back to that same load test. I go, you slap memcaches again. So fun. I'm indebted to, I wish I should know who came up with that name, but
the hardest problems in computer science, and also the most gratifying.
We were able to find, so remember, we started out with these dinky little R2 2 extra larges, a lot of memory, not a lot of CPU. And we were able to find a version of using these big 4 extra large hosts. We had these 16 core hosts, much beefier than the little ones, but we were able to find a way to get about 93% of the throughput, almost full throughput for this giant beefy host compared to this little tiny host again, by using this, but encrypted. Yeah. So, and it's just kind of wild how much CPU it takes to encrypt things. But it just does. That's life. How we ended up laying this out, and I think this is kind of fascinating, but sort of makes sense if you think about it. We used 5 cores dedicated for Memcache. So Memcache is running 5 threads. Its default is 4. We found it was slightly better with 5. It's not a lot better with more for, I don't know, reasons.
Interesting.
5 more cores for encryption and 5 more cores for decryption. And then we left the 16th core around idle to do stuff like for kind of admin stuff for like chef runs and Nessus security agents and just like stuff that needed to happen that we didn't want to get in the way of the running state of the machine. So, but it kind of makes sense if you think about it. Like Memcache can do stuff, right? And then it can get a request and it can send a response and it can do stuff. And so there being a symmetry of like worker threads and encryption threads and decryption threads sort of makes conceptual sense.
It is pleasant. There's a pleasant symmetry there
because not like the doing things doesn't take any time at all, right? So you could have more Memcache threads, but they wouldn't have anything to do because they're busy sitting waiting to receive and send network traffic.
Stuffing things really out of memory is not that complicated, I guess.
Yeah, but we did find that there was a benefit to having one. Like fewer Memcache threads was marginally worse, but mostly it was the CPU. Okay, so now we have this same 540 hosts or whatever running. We have to reprovision them because reasons, like in order to configure them properly, you end up just having to reprovision them. And so I have to go make the donuts again but then we turn it on and like it's sort of like underwhelming, right? Like it worked fine. It was fine.
Yeah. Hey.
Yeah. So
but actually, yeah, that's fantastic.
Yeah, it's great. Yeah. So it was like not that exciting, but that's what you want in infrastructure work, right? You want it to be boring. And it was finally after it ended up being about 4 years start to finish. Like everything's working. Cool.
Dozens and dozens of rounds of donuts.
So many donuts. And I kept having to make the donuts because security tickets keep on coming, right? And mostly the prescribed fix was reprovision your hardware with the latest whatever, with the newest AMI image. And so I was just making like once a month I had to make the donuts, and that was very cumbersome. And my wife keeps saying like, can't you have computers do this for you? And I like, yes. And we can go back and look at that architecture diagram I wrote in 2018. And it's still true that would do this for us. But until you have confidence that that you can reprovision these hosts at some regular cadence without people watching to say, yes, it's okay to do it again. We didn't have that. It was still kind of bad when a host restarted, and so you still had to like it was fine, but you could tell, like you could watch the charts do this, and like
that's you were inducing errors in the system. Every stuff would fail,
like
and
every security update is a mini outage. And so this dovetails now with the work that Mark was doing to get McRouter back up to date. Because along that journey, he did eventually get to like a single McRouter sidecar running with that we could build and modify. And in doing that, we were like, this is fine. We don't need to fix it because it's fine. We just needed a newer one, and we needed to solve these 3 or 4 ways in which we were misusing it. And those are kind of fun to talk about. I know you saved like what are the weirdest bugs you ever found for the end, but I'm going to tell you some of them right now.
Let's do that. What is the weirdest bug you found?
Well, so the bugs that we really couldn't explain would be like, we would do these tests where we would take down some subset of memcaches to prove that we were resilient to a availability zone failure. So we would like block them, and what we could never understand was what you would expect naively is that all the traffic going to those hosts would fail, and that percentage of the key space would not be in memory, and you'd fall back to the database, and like it would be bad, but it would be like 30% bad, right? But instead it was always 100% bad. Everything would always break. And moreover, so we actually had the caches, we had several different cache pools at the time, and a really startling finding was that if you broke one of the cache pools, requests to all of the others would also fail. Like literally, like all Memcache usage would break as soon as some small subset of it started to. This was a mystery, like for literal years, this was a mystery. And we finally figured out, so I think I mentioned that the HHVM, which is the runtime that houses the hack language, it's anyway, HHVM has a little built-in McRouter that is how you talk to Memcache through HHVM, which is
okay.
You don't have to. There's this other. It's a good time to mention that we had 3 different hack libraries for talking to Memcache. There was this very, very old one that came along from Flickr, like Cal Henderson wrote it in ages past, right? And it actually was part of the initial code dump from Flickr into Slack. It was a decade old. It was called libcache 2.
That's what you started with. You started on libcache 2.
Some smart aleck wrote libcache, which was to be its replacement, but actually just proxied to it and afforded a few different interesting access patterns. But there was no effort was made to port anyone to it. It was just like, here's this other differently, confusingly named library because it's actually newer than libcache 2. But anyway, and then there was this other one called source cache, which was part of the broader effort to stop having our code base look like PHP that had been ported to Hack and start making it look like Hack, which was in its own, like, it can be a very nice code base if you use the kind of affordances they give you. So all 3 of those live at the same time. And there is kind of Slack was a very marketplace driven, like the best solution will win kind of places. And none of them was a particularly good solution. So none of them won. So there were just 3 and people used whichever one they stumbled upon or whatever one they copied the code that they were going to use from. Or anyway, source cache, which was the eventual winner through effort, and we'll get to that effort later, used this little local sidecar McRouter to do its stuff. What we eventually learned was that, like, the way you configure McRouter matters, and default configuration matters, and the default configuration that we had sort of accidentally used through assuming that the defaults were sane was insane.
Go on.
So the sidecar McRouters we had configured consciously, like every different whistle we had looked and said, what does this bell do? We'll turn this on. What do these do? And so these are little processes that run next to the web app on the same hardware, and they take care of talking which Memcache to talk to. The local McRouter that runs inside was just stock. And the most interesting, the first thing we found that was this thing called TKO, technical knockout. And the idea is you're talking to a bunch of Memcache hosts, and one of them has started to act poorly, right? It's timing out, it's slow. After a certain number of errors, you're just going to say, that one's bad. I'm going to stop talking to it for a while. You bad. I'm going to stop talking to you for a while, go in the corner, get better, and I'm just going to quickly fail all of these requests, because failing quickly is better than waiting to fail when you know that failure is inevitable. Right?
Sounds like
a good idea, right? So that's great. The in-process McRouter in the HHVM talks to the sidecar, which is a single host.
Oh no.
Yeah. So just the one, right? And so when it's behaving badly and you put it in a corner, what you have done is put all the cache traffic that flows through source cache in a corner.
All Memcache decides Memcache doesn't work. All 540 hosts. So
not all of it, because remember, there's 3 cache libraries and the other 2 are immune to this particular, but enough, right? Enough to make it really bad. Like the whole universe topples when that much of your cache isn't working for you. There's an other side discussion about where don't make your system fall over when cache goes away, make it slow and make that be okay. But that's a big other topic.
That's a separate. Yeah, that's absolutely
That's
thing,
a whole other
but
ballpark. So we fixed that. We made TKO go away. Great. We like turned the disable TKO flag on, and we defaults matter, right?
Yep.
And we found that we had fixed it kind of, but we still saw these big hourly spikes. We would have high throughput traffic, and the older cache libraries worked fine, and source cache just fell over at the top of the hour on all the hosts. So we still didn't understand why. And okay, so defaults matter. The McRouter has, the sidecar has 4 threads. Yeah, that's enough, right?
Mhm.
It has these 4 threads, but actually what it is that it has 4 threads for each host it talks to. So that's like a lot of threads, right? That's a lot of concurrency available. And it makes sense, right? You might want to talk to the same host a couple times concurrently for something. So
Yeah.
having some, that's fine. The sidecar has 4 threads, or so 4 threads per host. The in memory one, the HHVM local one, also has 4 threads per host. Like, this is the same problem, right? So whenever things get really busy, it very quickly saturates its 4 channels of communication to the sidecar. Everything stacks up, everything blows up, yeah, right?
It's almost better to have TKO turned on if you're going to have that problem too, right?
Well, it's like a soft TKO. Like, it's not as bad as TKO, but it does cause this backup. And HHVM, because of the threading model, doesn't handle blocking stuff very well. Like, it just runs out of threads and says and so we fixed it. What we ended up doing is we did a bunch of experimentation, and we found that kind of 8 threads per core of the box was the sweet spot. So if the box says 4 cores, then you've got 32 threads to do your memcache, to do your, and that tended to, like, more than that started to have a lot of contention. Less than that had more of these kinds of stacking failures at the top of the hour. So I went with that, and then we made a very thorough audit of the defaults for McRouter.
Twice burned, 7 times shy.
Yeah. It's I'll just note that the way we figured all this out, and actually the way that Mark was able to very carefully migrate to this new McRouter, was that I mentioned that we labeled all the we had all of this Honeycomb data. We had in the web app this thing called we had feature flags, which I think are a fairly common idea now, but just things you turn on and off to affect different behavior. It's delicate to do because the feature flag system itself was initialized using Memcache, because it was kind of smashed together with the experiment framework, which used Memcache to figure out what experiments to run. So we had to kind of end run it to be able to have kind of lower level feature flags that didn't require any other smarts. I didn't want to label all the traffic with every single feature flag, because that seemed like that's a lot.
It's a lot of flags.
So we wrote this little goofy thing that would take all the flags we cared about and assign them to this little bit field. And I would just always write this bit field that had the things turned on and off and on and off. And Honeycomb is amazing because you can derive fields from other fields. And so we were able to come up with like sort of pseudo labels that said this feature is turned on, that we just kind of derived from that bit field. But we were able to tell how we even knew that source cache was the one that was being more badly affected, was that we sliced on everything. We sliced on library, we sliced on hardware type, we sliced on the way I was able to derive 8 threads per core, was that we had all the data labeled with all of our different threading experiments. So we could compare success rates, we can compare latency. We could learn that during this McRouter upgrade, we found ourselves a 9 in availability.
Oh, cool.
We didn't even know what our availability was before we did all this, right? But so it's really amazing that the power of being able to see what you're doing.
The 9 was at the front of the number, I assume, right?
It was the good 9. Yeah.
Okay.
We went from 4 to like 5.5 as a part of this effort.
That's real.
But I'm still making donuts every month, right? But these are the sorts of fixes we needed in place to be able to be like, a system of automation feels safe to run now.
Mm-hmm.
And so this is when I start to go off and decide I'm going to build, or sort of in parallel with this, as we're arriving at this, like, we trust our system now. How can we get rid of our unenduring toil? I started to think about the system that would replace the janky leader election thing, Python 2 leader election thing, with a system that would use that lever I talked about at the very beginning of the episode of kind of fast distributed configuration management. And we called it McRib, which credit to my coworker Chris Sullivan for coming up with I think we sort of workshopped the acronym, but he figured out that we could actually call it that and call it the McRouter, the Memcache Routing Intelligence Boss. And so McRib was to be the system that would, because as an aside, we had to upgrade this thing, the Python. We had a Python language version end of life deadline, and we really didn't.
So did we all.
Really didn't want to. Yeah, right. You managed this, right? We really didn't want to upgrade this terrible thing. We didn't want to like make a new terrible thing if we didn't have to.
But last week's episode was Lyft's 2 to 3 migration, and it was not trivial.
It was gross. And the best way to migrate something is not to migrate something if you can.
Oh, absolutely. We would all prefer not to touch the software ever again. But
also this, so like, and now we're a little bit in bad to good territory here if we're not careful. There were lots of bad things about this beyond just the version. Chiefly, like, anytime it would restart, Memcache would forget that it had been a member of whatever slot it was, and its slot would be given to somewhere else, and it would cause like a little micro outage. Sometimes they would do chef runs that would take down the whole tier of this little leader election script, which would basically cause a full election of the whole ring over again, which would cause a huge site outage. So it was very delicate. We had no way to version it or restart it or deploy it that didn't cause an outage. So McRib was chiefly there to like fix that, to make to have a system that we understood and could operate that would be in charge of delivering configuration to McRouter to know which memcaches to talk to. Just that. And I think that part was fun. Go off and write some Go, and that was a lot of fun. The interesting part is getting onto it, right? Because the McRouters currently eat this JSON configuration that's from a rendered console template, where the template itself is an ERB file from Chef. So there's like Ruby templating going on too.
Mm-hmm.
And like multiple layers of variable injection. And like, so the first task is like, can we make a file that looks just like this file? And can we deliver it? And can we deliver it right next to it on disk and with some confidence? And so the first thing that McRib had to do was it itself became a consumer of that config file. And all it did was eat it into its understanding of like its domain objects and spit it back out and ship that everywhere. And so all it was a pass through, but it was a pass through that went through McRib logic so that we could prove that we understood the primitives that we were dealing with.
Yeah, that makes sense. Did you find it? Were there any like load bearing bugs?
Oh, and no, this was actually, not really. I was very happy that nobody cared about white space, or trailing commas, or because all we did was go from like the config file was written out with Go templates. So, and it's like notoriously hard to get the white space right. But we did, like, I think it was the only biggest bug was that it was a load bearing decision, right? Which is that McRouter uses JSON-C, which is called JSON with comments. And it's a superset of JSON that allows comments and trailing commas. Or I think it actually requires trailing commas. And so you have to, there's an extra layer of like weird library jank to support JSON-C and Go, because it's not part of the built-in JSON marshalling, but there's a nice library for it. Anyway, so we get that in place. We're delivering the thing. We're eating it and spitting it back out, and that's all working fine. And then like the way that McRib works is it sniffs service discovery, so it knows all of the Memcache hosts that exist. It knows the last version of the config file, which says which hosts were where. And then there's always 20% or 30% of the hosts that we just keep spare, ready to take over when bad things happen. And the trick is you want always to compute the minimum different config, right? So you want your config to look just like the one before, but with just this one host that went bad replaced. You don't want to recompute the whole ring, because that now all the keys are in the wrong places, and you've caused a big outage. So the delicate step was going from I'm reading from the old leader election script to I'm reading from service discovery, and I'm definitely producing the same result either way.
Harrowing.
That was but we did it incrementally, right? The first thing we produced both and diffed them for a long time and made sure that diffed them in McRib and like complained in a Slack channel if they were wrong. And
so you're pretty convinced that it was doing the right thing.
We knew it was going to, but there's still like the next deploy of McRib is turn it all on, and now you're drifting, right? You're somewhere in there with, like, I guess actually the first step is ship them both so they're next to each other. Second step is get all of the McRouters to start eating the new config file instead of the old one. Third step is cross your fingers a lot and flip the switch and start reading from the new, like making the new system authoritative. And then those two files have to drift. So if you roll back, you're kind of like, you really can't roll back.
Yeah.
You just can't.
So there's a point of no return.
Yeah. And most of what we had done to date, we could turn off if we had to, but this was really like, once we had made the switch, there we were. And thankfully that was very scary. And thankfully that worked okay.
How long before? So you switch and then the system starts to drift. It's not drift in code. It's drift in like production reality, right?
It's right. Over time, a Memcache will go down, and which spare you picked to fill that slot is different.
Yeah. So what did you have? Did you 5 minutes, or did you have like days? Like how long was that drift before you were really, we can't go back?
I mean, as soon as a few of the hosts are different, it's your and that they don't fail that often. So we were largely, but they fail. You're not in charge of when they fail. Right?
So you didn't know going into it.
So we didn't know, but basically we kind of declared victory. And I mean, at that point, there's no point keeping it around, right? The system we have was in kind of in every respect easier to reason about. And so if it was broken, we were going to fix forward from that point. Like we weren't going back. And so the rest of the process is like clean up all that stuff and get rid of the leader election and stop using console in this bonkers way and get rid of all these console templates and get rid of all these ERB files and clean up your mess. But like the win here, the good part is now I'm not yet out of donut making, right? But it's for the system is responsive enough. McRouter works well enough. We understand Memcache enough. We have all of these ways of seeing how it's behaving. We have the right alerts in place. We have all the things we need to know when something's gone wrong. And we have a very reliable system for recovering from that. And so the thing we do that's fun is we just we had this thing called ASG tester, and its job is to turn off a host in a autoscale group in AWS and replace it with a new one. Like that's its whole job, is just prove that provisioning a new host works. And so we said, what if we just did that, but like all the time, and we'll just cycle through all our hosts every few days, or whatever, at whatever pace seems good. We ended up doing don't do it in the couple of hours in the morning where things are very busy, because it makes people right. But
you're controlling when you induce this stress, but not incident level stress on the system.
But it's basically like host reprovisioning in cron. Think of it like that, right? And all of a sudden the donuts are making themselves, right? Like because when somebody files a security ticket, I say that's fine, because in a week it'll just all those hosts will be gone. All those security tickets are gone. And then the grunt work became closing the tickets. But thankfully secure, a lot of folks got wind of this, like, hey, if you reprovision your stuff all the time automatically and that works, like security problems go away. We championed that as a best practice. And so it became SecOps' problem to make those tickets go away when they were no longer true, which is great.
Amazing.
And so
cool.
So that's a toy. So we've done like the mandated migration of technology, and we've done the toil migration. And the coda here, if we have time, is to talk about those 3 cache libraries, and how we got to the 1 cache library.
Yeah, let's do that. Let's do that quickly. We should wrap up.
Yeah, that one's pretty quick. And I'll caveat that I wasn't actually all that involved in it. But broadly, there was no incentive to switch from one library to another because they were all kind of fine. In theory, source cache prevented certain kinds of thundering herd use cases because it had a way that you could fetch something, but if it was missing, you could basically coordinate with everybody else to decide who was going to do the filling. Mm-hmm. And if it wasn't you would just wait, and then eventually it would be ready or it would time out. You can see some problems with that if you think too hard about it, but don't. Source cache also had an envelope around the cached values where you could do things like version numbers and some metadata. So you could do things like, we want to change how things are cached. We'll just flip the number and now we know whether it's a new or an old value and stuff like that. So it was kind of useful. But there was no incentive to do anything with it. And it wasn't really a priority for anyone. So it was just kind of bad, but I guess it was an okay, right? It was okay to good. It was okay to good. There's always bads, right?
So what happened?
Well, so if you'll recall, you yourself shepherded a project wherein we wanted to make full stacks of requests be a local to availability zones, so that we could route away from an availability zone with a bad network situation, and all the traffic would just silo in all the other zones, and it would be fine.
We were in a bad state. Amazon would sneeze for 30 seconds and induce 2% packet loss, which is real, don't get me wrong. And Slack would be hard down for 4 hours because we would just...
it was kind of like with my Memcache thing, where like if one goes down, they all go down. Like it just created a problem that was so like just enough bad that it became bad everywhere. And so one of the things I loved about McRib was that it let us do things like ponder ways we might differently configure a McRouter at all, which was not possible before because it was so cumbersome to change the config templates. With McRib, changing config templates was a deploy, and it was easy. And so we cooked up this config that would let you access this big 600 machine cluster that we talked about before, either as one big ring or as 3 small AZ specific rings. So same hardware, you just can decide whether you want to talk to the keys across the whole thing or talk to the keys locally. And it's kind of neat because so like your total traffic, we had so much extra memory because we were, if you'll recall, just grossly CPU bound for the
right
for the encryption traffic. So we had all this extra memory lying around. So it was like fine to store everything 3 times. We still had way more memory than we needed.
For once, you managed to fail your job of spending more money.
Yeah, right. Yeah, it was like, oh, here's the code. Like, here's the payoff is that now I can spend that same money, but in a way that makes us more resilient to AZ loss. And also incidentally, like we shaved off, we went from like a millisecond to like 2/3 of a millisecond for most requests because the local hop was much shorter.
Yeah. Memcache requests are just in a totally different ballpark of every other RPC in a system.
Yeah, they have to be basically instant. They have to act like memory.
Yeah, everything else is measured in tens of milliseconds or single milliseconds, and microseconds.
We didn't really talk numbers, but that Memcache cluster did tens of millions of lookups per second at
wild.
Yeah, it was
real volume.
So it turned out that in order to use this AZ stuff, you kind of you had to opt into it. I didn't want to just turn it on for everybody because it restricts certain use cases. And our cache was kind of Wild West. Like an example of a use case that would not work at all is people used Memcaches for mutual exclusion, like for locking. Like, I'm going to grab this key in Memcache, and that means I can do this, which, by the way, that's a lie, because the cache can go away anytime. So it's like
Cache.
It's kind of hopeful locking, right? It's not even optimistic. It's just hopeful. But if the lock you're grabbing turns out to only be an AZ local lock, then you're not really excluding it. There's two other friends of yours who are going to be doing the same work.
Right.
And so there were a bunch of those kinds of edge cases where the access pattern just didn't make any sense in if you were going to be AZ local, because you no longer could guarantee that the data you were looking at was the sole place that data lived. And so it required people to do some thinking, but was also a company priority suddenly. And so we had a cudgel with which to prod people along. And we realized that because people can only do a certain number of migrations at a time, and asking them to do, like, Slack was sort of notorious for always having 4 or 5 big migrations going at a time. So it wasn't strictly necessary to move to source cache to use the AZ local stuff. As a pragmatist, I made it work with both, because I wanted it to be a system that we could actually ship. And so I went through porting some of the really big Cardinal, like, high throughput keys on using both libraries to prove they worked, and everything was fine. But it was sort of a convenient cudgel to say, well, if you're going to do this AZ local thing, which we are telling you have to now, you might as well go to source cache, because it's not really very much more work, and you get these couple of little things out of it. And that mostly worked. That was what I wrote. A big run book for how you do this port. I wrote a run book for how you tell if you're one of those use cases that is not a good candidate. And there were a few, and they're like, too bad. Like, your answer is, I'm just not going to work right when we do these AZ failovers. And okay. But then it became like a gnarly TPM spreadsheet of all of the different codes. It became like the thing you want to fix, right? It was that.
Yeah. And this is exactly one of the stories that I anchor on. And you mentioned Ryan Greenberg earlier, and he's my co-founder at Turn.
And he did a lot of those migrations. He did a lot of the, like, let me see if I can solve all of these in one pass with code modification tools.
It's running that run book manually in 2025 when LLMs and AI exist. Seems dated, right?
Certainly, like I hopped up as the final coda here. I hopped off the bus here just as this process was getting underway. Number one, because my job, like, I had found a team or kind of built out a team that were the right people to own all of this stuff. They own some other stuff too, but it was like of a piece with what they own. So I had a team that I trusted to run McRib and to understand Memcache. They had all the right tools in place, and I was tired of being on the hook for a tier 0 service after 2 years. And so I kind of stepped off and went off and did some other stuff. After my last deliverable was those run books. Right? And then it was like, this seems like a kind of a boring problem now to actually get people to do this. This is not or if not boring, at least not something I'm good at. So I'm going to go do interesting engineering work and hope that, like, the system of grinding people into doing labor works. But certainly if somebody could have just pushed a button, it's like a note, like, then my job of describing the migration becomes interesting, right? But also the last thing I have to do, which is what I would have wanted, right? Like, I would have said, like, here's how you do this. I've tested it enough times to be comfortable that it's going to work. You should feel comfortable just pressing this button and doing it.
It's one of the, I think, undersold things of automation, and kind of a theme of what you've been talking about is that you wanted to automate making the donuts, but you also had to start with implementing it on a different system where it was more tractable, and then you had to do it manually a gazillion times while dialing in whether that made sense. Like, same thing for source cache. Like, you're not going to automate the first one; you're going to automate the 10th and beyond.
Right. Yeah. No, you got to try it, prove it works, find the things you got wrong, fix those, do it again. Yeah. And get it to where it once it's a crank you can turn, it doesn't make sense for people to turn the crank anymore than it makes sense for people to, like, I don't know, power turbines. Yeah. Right? Like,
hook it up to the generator and turn the crank. Have the crank be turned.
But it has to be donuts you're making, and not, like, engine guns pointed at your face.
Right. Bad donuts are fine, to stretch the analogy a bit too far.
That's right. Yeah, but you have to get them to the point where they're harmless at least.
All right. I have two questions for you before we go.
Right.
We're starting to get into it now, but what tooling did you wish existed during this whole process?
What tool did I wish? I mean, I wished for Honeycomb, and it was there, and so I was very glad to have that. I could not have done this without tracing. The magic that is always promised, and it's so far yet to be delivered, even with AI, that is like a robot to watch the charts for you, like AI that knows when something truly has gone wrong. AI that can correlate to charts that are in their domain very far away, but have exactly the same shape in a way that's like, I mean, this is like, it's reasoning stuff, right? Like it's what made the job hard was understanding why those two charts were the same shape, mostly.
Yeah.
And so, and what made donuts making hard was knowing when it was okay to keep going. And so it would have been really neat to have, and we tried but like for I don't know, 15 years of working, I watched people try to use machine learning and kind of like sort of pattern analysis to be like, they send a page when it's like, hey, this looks wrong. And what you get is a channel filled with pages you don't know what to do about. That are always either too noisy or not noisy enough. So that would have been really nice, I think. I don't know. Mostly that, like the tools I was using were all fairly simple, and it was like, I think was interesting for me about this project was the like none of it was hard exactly. Right?
Except,
none of it,
except the understanding,
except
and the correlation.
All of it, right? But there's no single technology was difficult to comprehend. It was just that the totality of them.
How long did it take you to figure out you should turn off TKO?
We started in 2021, in like spring of 2020. It was probably a year before we found it.
It's not hard to do. It's hard to figure out.
Well, there was so much else wrong, right? Like you have to like cut away all the obvious wrong before you can see the really interesting wrong, right?
Yeah. Cool. And last question: if people want to follow up with you, is there a place they can find you on the internet?
I mean, I'm a little bit of a hermit these days. My website is glen.nu, and is in Nancy, U is in umbrella.
We'll drop a link below.
Yeah, and there's a contact form there. You can get me that way. I'm 9len on X or Twitter, but I don't really use it anymore. I can't even remember what I am on everything else, because I'm just not that active in all the different ways one could be social right now. But I'm easy. I'm easy to get in touch with, and I love to talk. So
awesome. Well, thank you so much. That was a fascinating story.
Thank you.
I'm so glad we could make this time.
Thank you for your patience with we're really quite a long endeavor.